Okay, today we want to continue talking about stereochemistry of reactions, how we deal with the problem of being able to separate enantiomers. And recall from the last time that we talked about diastereomers as having different physical properties, different solubilities, different melting or boiling points, different issues like that allow one to use those physical properties as some method of separating diastereomers. But enantiomers don't have that ability. So when we think about trying to separate enantiomers, we have to think a little bit more carefully. And so it's important to understand excuse me, the consequences of reactions in the formation and creation of stereocenters so that we can get an idea about how this works. So just to recall, we have all kinds of different isomers, but in particular stereoisomers, which are either mirror image isomers or diastereomers. And remember, mirror image isomers have identical physical properties. Diastereomers could potentially have different physical properties. So that allows us then to be able to separate. Whether those are configurational diastereomers where we have more than one stereocenter and they're not all mirror images of each other, those would be configurational diastereomers, or cis and trans, we have the ability to separate them based on how they interact with a solid phase in chromatography, or different solubility, or different melting point, or different boiling point. So from last time we talked about this reaction, this reaction which happens to be a stereospecific reaction, not stereoselective necessarily, stereospecific. That is, when we have a double bond with a specific geometry. And if you think about this double bond, it has the cis geometry. It's tied in a ring. It can't orient one way or the other. If we do a reaction which allows reaction to occur in only one side of that double bond, like the formation of a bromonium ion, the reaction could either occur to open the bond on the left or on the right side, in which case we would form the product to the left, or this bromide could attack the carbon, breaking the bond on the left side of this bromonium to form the product on the right. These are related as mirror image isomers. So you can see there's a mirror image. This happens to be, let me get this right, this happens to be the S configuration and the S configuration. Is that right? Yes, S and S. This happens to be the R and the R. So those are enantiomers, and the only way we can do this reaction is to produce a 50-50 or racemic mixture of these two, because there's nothing else chiral to influence. These are enantiotopic reaction pathways, whether it goes and attacks the carbon on the right or the carbon on the left. Since this molecule is completely symmetric here, there's no difference in energy for those. So you can only form a 50-50 mixture. It is stereospecific. Well, let me just go beyond a little bit what we talked about in the last class, and that is, let me erase all this for you, and that is, what if we do this reaction? Remember the reaction where we can take Br2 and H2O? Now, instead of bromide, it's water, which is adding and resulting in the formation of a hydroxide compound. So again, if these two pathways are carried out, it's this now versus this. Okay. Now we still have mirror image isomers, but if we didn't have a symmetric ring, this situation would be a little different. And I want to talk about that on the next example in the next slide, because if you take a look at this example that we talked about with cis-2-butene, okay, let's take a look at this reaction now. This forms the bromide with an SS or an RR. Those happen to be mesomolecules, especially if you rotate this bond up. Well, sorry, those are not mesomolecules. I have to be careful not to mistake. These are mirror image isomers. They are enantiomers. And those enantiomers then are formed. You wouldn't be able to tell, actually, if you do this from one way or another. But notice what happens in this case. In this reaction, we add Br2 to form a bromonium ion, again, across that double bond, right? And if I'm looking sideways at this, with this being in the plane, I would have two groups coming out on those carbons and two groups going back. Two of those are CH3 groups, as is shown here. I'm just going to leave them blank here, but the other two hydrogens that are not shown are here. So if you take a look at this bromonium, right, the next bromonium ion could add, or the next bromide could add either here or here. That would form one enantiomer or the other. Okay, I want you to notice very carefully. This is the SS and this is the RR. Okay, these are enantiomers. If we start with the cis-2-butene, we form the SS enantiomer and the RR enantiomer in a racemic mixture. Okay, what happens if we start with the trans isomer? Let's go back and look at that trans isomer again a little more carefully. Okay, here's the trans isomer, and if I carry out that exact same reaction, let me draw the intermediate bromonium to show you. Okay, here's the bromonium intermediate. Again, we have a group coming out and a group going back. Group coming out and a group going back. Now, since we start with the trans double bond, okay, on the left side of the way I'm picturing this, we have a hydrogen coming towards us and the methyl going back. And on the right side, we have the methyl coming towards us and the hydrogen going back. Notice the consequence now when we add the second step to this. We actually form a meso molecule, and if I draw it in this configuration, you'll see that. But the relationship of this molecule, of course these are identical, but the relationship of this molecule to the one on the previous slide, starting from the cis isomer, is a diastereomer. So if you look at this, this is the S configuration, and this one is the R configuration. So we have S and R, and here we have R and S. And since we can number the molecule from one side or the other the same way, 1, 2, 3, 4 from either direction, we have the same molecule. It's meso and symmetric. Okay? But this molecule is a diastereomer to the molecule product on the previous slide. Now, we no longer have a meso compound if we do the reaction in water instead of with the Br minus, and you have the water add and we get the hydroxy group. We will have an OH group or an OH group. Now these are no longer numbered the same from one end or the other. The molecule is no longer symmetric. There's no plane of symmetry. Okay? These are now enantiomers. So keep in mind, all the different levels of symmetry that we could have in molecules impact what we actually observe in products and reactions, etc. Okay? Now, this is where we left off in the last lecture, talking about a case where we have a reaction on a double bond. It's a stereospecific reaction. We only get the trans addition of bromine across the double bond. But that trans addition could be in two different ways. Okay? And in fact, these two happen to be diastereomers of each other. One configuration, notice the CH3 group, the carbon that's attached to stays exactly the same. It's the other two which change. So overall we have 3 stereocenters in the product. One stays the same. The other two are switched. So they're not mirror images, they're diastereomers. And in each step, the influence of the chirality, or the nature of the asymmetric group, that is this CH3 group, makes one side of the double bond different steric environment than the other side of the double bond. So as the bromine is coming from the top or the bottom to form this bromonium, we have two possibilities. Notice these groups on the top of the ring here is smaller and the CH3 is larger. So the bromine as it approaches will come from the side that's easier to access, the one that has less steric crowding. So we will form selectively this bromonium as the major product and this one as the minor product. That's a stereoselective reaction. The stereochemistry of one chiral center influencing the generation now of new stereocenters. And so notice these carbons that we form in that process are stereocenters. They're stereogenic carbons. So we can get selective formation of one configuration over the other configuration. Okay? And that's important to recognize. One configuration over the other configuration. And so we get a selectivity. So we have a major product and a minor product. And then either of these could go on to form the bromine adding on this side or this side. That second step also is influenced by the group which is attached. It's harder or less crowded or higher energy. I'm sorry, more crowded or higher energy to add on the left for this bromide than it is onto the right. So we would expect this to be the major product from that compound and this to be the minor product from that intermediate. Now, even if this other isomer here is formed in a little amount, it's still there, and there's not much to distinguish the differences on the top side here in that second addition. So we would probably expect from this one would be less selective to get both of those. So the situation, if you really analyze each step and each possible product formation, each stereoisomer which could be formed, you have to really think carefully about what influences the formation of each one in each particular step. Organic chemists do this all the time. We're constantly thinking about all of these issues when we design new reactions or try to do something that's very selective. Okay? All right, well, let's talk about enantiomers and how we separate them. This is a process which we refer to as resolution because we've resolved or separated the mixture of enantiomers. And the first real documented case of this was the example I showed you at Monday's lecture, which is the example of Louis Pasteur. Because the two enantiomeric salts of the tartaric acid crystallized in mirror image macroscopic crystals, something that you could actually see with the visible naked eye, he was able to use tweezers and separate enantiomers. In other words, he resolved the enantiomers of sodium ammonium tartrate. That is not so easy to do, and not every molecule and its mirror image will crystallize like this. Sometimes you get crystals in which the molecules pack in a racemic form in one crystal. So there are many, many different ways in which that crystallization could happen. Again, they don't have different physical properties necessarily, but in the case of this particular molecule, one enantiomer happens to pack together better with one enantiomer than in a mixed enantiomer environment. So we get mirror image crystals. Okay? So the idea is if we really want to separate enantiomers, we need to find a way to change the relationship from enantiomeric between molecules to a diastereomeric, and that is by adding some other chirality. Okay, and we can do that either through ionic bonds or we could do that through covalent bonds. So I'll just share a little bit of that. Here, for example, let's say we have a mixture of these hydroxycarboxylic acids. Okay, this has a single stereocenter, and we have a 50-50 or racemic mixture. This has a carboxylic acid functional group and then an alcohol functional group, and the configuration is exactly opposite, R configuration and S configuration. They have the same physical properties. Okay, but let's say we have on the shelf a bottle of this particular amine. It also has a stereocenter. It happens to have the S configuration. And fortunately, we have a bottle of this molecule, which is a single enantiomer. It's optically pure. Okay. Now, I don't care that you really understand all the chemistry right now, but I will say, since we have an acidic, a Bronsted acidic, or a Bronsted acid site on this, a carboxylic acid, and we have a nitrogen with a lone pair, which is a base, we can have a proton transfer occur. Proton can transfer from the acid to the amine to make a carboxylate anion and an ammonium cation. That forms an ionic salt. Okay, but now we have an ionic salt that has a diastereomeric relationship. So if you look at the possible products, we only have a single enantiomer present of the nitrogen compound, and we have a 50-50 mixture of the acids. So what we have now is a salt which is made up of an ionic attraction between an R configuration of the acid and an S configuration of the amine. And then we have another one which is a salt of the S configuration of the acid with the S configuration of the amine. Okay? Notice the relationship between those salts are diastereomeric. Okay? We have a different mirror image of the carboxylate, but taken together, now we have two stereocenters, SS, and on the top one we have RS. Those could potentially have different solubilities in solution, and you could, in principle, crystallize one salt pair out over the other. Simply do that, and you separate them. You separate the solution from what crystallizes, and if you have enhanced amount, if you have only one enantiomer of the acid group in that solution as this diastereomeric salt, then you've separated it, you've resolved it. And all you have to do then is add protic acid to reprotonate the carboxylic acid and no longer have ions, and then you can retain or get back your acid and recover it. Okay, so you can form do an ionic reaction or a protonation acid-base reaction, form a salt which now has a diastereomeric relationship, separate them, and then go back by simply adding acid to remove base and protonate back the carboxylate. Kind of a nice trick, huh? It's used a lot in industrial preparations of chiral molecules, and since the ability to have single enantiomers in pharmaceutical drugs is very, very important for safety. The pharmaceutical industry that produces and synthesizes drug-like molecules uses this process a lot. Okay. Another way to do this is not through ionic bonds, but through covalent bonds. So again, if you have a racemic mixture of something and you react that with something else which has a chiral center, but it's enantiomerically pure or optically pure, then you can form diastereomeric compounds which are covalently bound. And that's the case here. This is a reaction which you'll probably study if you go on to 342. It takes an acid chloride, this is a carboxylic acid chloride, which is reactive and essentially reacts with the lone pair of the nitrogen to do a substitution of the chlorine for the nitrogen group. And so what you see here is the formation of a covalent bond in that product. But here again, let's say our nitrogen compound, this is the same one we used on the previous slide to make a salt with carboxylic acid. So let's say that one we didn't have pure. Let's say that one was a racemic mixture. We could have used a single enantiomer carboxylic acid again and made a salt, like the opposite of the one on the previous slide. Or we could form a covalent bond if we have a single enantiomer of something like this, which has a stereocenter. This happens to have the S configuration. So if you have a 50-50 mixture and react it with 100% of this, what you get is a 50-50 now mixture of diastereomers. They're no longer enantiomers because it's SS versus RS. One configuration stays the same, one is different. So now we have a 50-50 mixture of diastereomers, but they could have different physical properties. Just like the salts might have different solubilities, these might have different physical properties that we could use to separate them. And so that's something else we could do to resolve these enantiomers. All right. So chemists use this all the time. I do want to point out one other thing, and that is when we represent molecules using line structures, okay, and I were to write this molecule like this with just a single bond between the carbon and nitrogen, that's a stereogenic carbon. If I write those with no bold or dashed, it's assuming that I'm just not telling you what the stereochemistry is. You can't assume anything from that. It could be either, or it could be a mixed racemic mixture. If you want to indicate a stereocenter as a racemic mixture, rather than having to write both of them, one with a bold line and one with a dashed line, what we do is we use a kind of a squiggled bond. That means that squiggle means we have a 50-50 mixture of the two. One of them is up and one of them is down. So instead of having to write both of those molecules showing one this way and one this way, we can just write and then saying it's 50-50, we can just write a squiggled line for a bond, and that tells us that we have a racemic mixture. Okay, and so that's another representation to say something about the stereochemistry, not that it's pure one or the other, but that it's racemic. Okay, this representation with no indication of up or down or a mixture, you can't assume anything. Okay. Okay, and I just want to finish talking a little bit about other atoms. Other atoms besides carbon. We have focused on the tetrahedral nature of carbon because it's fixed that way. You have 4 bonds to carbon, it's tetrahedral, but we know that things like nitrogen can bond to 3 things, so we have the potential to have 3 different groups attached to a nitrogen. Okay? And that there's a lone pair on nitrogen which occupies space, so it's also an sp3 tetrahedral atom, this nitrogen. So this lone pair is in principle a 4th group, which is different than any of the others. So nitrogen compounds are inherently chiral if you think about it this way. Its mirror image would not be superimposable. Okay? But in practice, when we try to measure optical activity of these kinds of nitrogen-containing compounds, where they should be chiral at the nitrogen center, we don't measure any optical activity. It shows no properties of being chiral. And that's due to the fact that the nitrogen compound, that lone pair, since that's a hybrid orbital, notice there's a little lobe which we tend not to write oftentimes, but those electrons could exist on either side, and actually these nitrogen compounds can flip like an umbrella. It can invert like an umbrella through, say, a flat structure or something like that. Actually, and I'm drawing it this way, but actually if I were to continue drawing this, I would draw it like this: B, C, and A with the lone pair down. Okay, that's just this rotated. So it inverts, just like an umbrella on a windy day. It will turn inside out. That can happen because the barrier for this inversion, you don't have to move a group like in a carbon. You'd have another group there. You don't have to move a group, break a bond, and then move it to the other side. In this case, it's just electrons flowing from one side to the other, and these groups moving from up to down. And that happens very fast at room temperature. So just like the example from Friday's lecture of cyclohexane with a 1,2-dimethyl, if you were to freeze one of the chair conformations, there's no symmetry in it, but in fact it's rapidly equilibrating. The same is true with nitrogen compounds. They could potentially, if you were able to freeze it in one particular orientation, it would be asymmetric and its mirror image would be different. But in reality, especially at room temperature, and much, much lower, by the way, it's not much energy to do this, this is rapidly interconverting. So it's always a racemic mixture, if you will. So it shows no properties of optical activity or chirality. Other atoms also have a similar kind of property like this, but that inversion can be much, much slower. And even at room temperature, they might exhibit chirality and chiral properties. If you just go down the periodic table 1 to phosphorus, phosphorus atoms are similar structurally to nitrogen atoms. However, there's a higher energy barrier to this inversion or this flipping of the groups and the electrons. So actually at room temperature, not all phosphorus compounds are stable like this, but some actually do exist in one of these enantiomer conformations. Phosphorus can be chiral at phosphorus and show and exhibit the properties of chirality. Some sulfur compounds which are in higher oxidation states, sulfur, I know you think it's below oxygen, so it's divalent, but it could actually have more groups attached. Sulfur can exhibit a tetrahedral structure when it's in higher oxidation states, and also show chirality. And other atoms as well. Silicon is right below carbon. You can have chiral silicon atoms. You can have chirality on other atoms. The whole important point is that the molecule overall is different than its mirror image. Then it will be a chiral molecule. Okay, so this actually concludes the topics that I wanted to stress for Chapter 7, Stereochemistry. Important aspects of this are to be able to really visualize molecules well and understand their three-dimensional structure and know the differences between what things are symmetric, what things are asymmetric, because asymmetric centers may lead to new different stereoisomers for molecules. Okay? I thought I would just end with just a couple more minutes and show you some examples, and you can find this on my 2007 exam 3, and I'm sure you'll be looking at that before the next exam. There are some problems on there on stereochemistry, and so let's just take a look at some of these problems I had on there. One of them was figuring out configuration. So there is a drug called Tamiflu, which is a anti-influenza compound. And I'll draw the structure for you of Tamiflu. Tamiflu is a molecule which has 3 stereocenters in it. Okay, and it has a 6-membered ring. 6-membered ring has a double bond. There's a ester functionality here. There's an oxygen attached here that's bonded to another carbon group. Okay. Notice I drew dashed for the stereochemistry. There's a nitrogen group attached here. Nitrogen. Okay. With that on it. And then there's another nitrogen group, a different nitrogen group, an NH2 amine group here. Okay, 3 stereocenters. What are the electron configurations? Okay, so let's go through this. Let's first look at this one on the right. And remember, the hydrogens I didn't show, so this one is coming up, this one is going back, and this one's coming up. The hydrogens are all the lowest priority group on these 3 stereocenters. So let's first take a look at the one on the right with the NH2 group. I'm going to go through this a little quickly. If you don't remember this, you might want to go back and look again. But we have nitrogen, carbon, and carbon. The nitrogen is going to have highest priority, 1. The carbon, well, the carbon next to the other nitrogen, attached to the nitrogen, is going to be 2. This is going to be 3. And the hydrogen is number 4. Now, since the hydrogen is coming up towards us, and then you go counterclockwise from 1 to 2 to 3, you need your left hand pointing your thumb up with that hydrogen to do that stereocenter. So that means that would be the S configuration for that nitrogen NH2. S configuration. Okay. Let me get rid of that one. We'll look at the next stereocenter. Here we have highest priority 1. Okay. Now, which has higher priority? This carbon to the right or the carbon to the left? Well, they're both carbons, so you go out next. One is attached to nitrogen, one is attached to oxygen. Right there you should be able to make a distinction. The oxygen has higher priority than nitrogen. As you go across the periodic table, it's carbon, nitrogen, oxygen, and then halogens. So this will be second priority, this will be third priority. The hydrogen is going down. This will be clockwise. So this would be, the previous one, did I say counterclockwise? Yeah, I meant clockwise. This is going clockwise, so this is the R configuration. Okay. And then finally, for the last example, oxygen is number 1. Okay, the carbon with the nitrogen is number 2. This is number 3. We're going counterclockwise, but our hydrogen is coming up. That's the R configuration. So this has S on the right, R in the middle, and R on the left. If you have any one of those stereocenters switched, this compound called Tamiflu no longer influences the influenza virus. It doesn't kill the influenza infection. So drug-like molecules are very, very important. Okay, let me draw some more molecules, and I want you to tell me the difference in their relationship. Are they identical molecules? Are they enantiomers? Or are they diastereomers? So let's take a look at comparing two molecules. Okay, so here we have bromine, and here we have chlorine. Okay, and let me draw another one. I'll draw it like, shoot, that's not what I wanted to do. Let me erase that. I'll draw it like this. Okay. These both have 2-chloro, 3-bromo, 4-methyl pentane. Okay, but I have stereocenters. Notice the one with the methyl is not a stereocenter because the 2 methyl groups are identical, so that carbon doesn't have 4 different groups attached. But let's take a look. I've oriented these slightly differently. Can you tell me what the configurations are? Are they diastereomers or are they enantiomers? Okay, so let's look at this. If I look at this stereocenter with the bromine here, I have 1, 2, 3, and the hydrogen going back, going counterclockwise, so that's the S configuration. And the chlorine, 1, 2, 3, that's also the S configuration. Okay? The molecule on the right has bromine, 1, 2, 3, going clockwise, but the hydrogen is up, so that's the S configuration. So even though it looks different, I've reoriented the molecule. The carbon with the bromine on it has the same configuration on both of them. Okay. This one, on the other hand, 1, 2, 3, has the R configuration. So we have S, S, and here we have S, R. We haven't taken the mirror image of both, so they must be diastereomers. Okay, diastereomers. Okay, here's another example. I'm going to do 2 more examples, and then if you want to do more, there's some on that sheet. Okay. This is a molecule with 2 stereocenters in it again. And I'd have that one, and let's compare it to this one. What is the relationship? Well, it's a little difficult to see because what I have done here is tricked you a little bit. I made you really take a close look at the molecules. And I'm going to just highlight the carbon backbone here in red. Notice my carbon backbone is in a open chain formation, and this carbon backbone is in a different conformation. I've just drawn it differently, but since these are all single bonds, there's always free rotation there. So what I've done is actually rotated around that middle bond to get to the other molecule. So you have to be a little careful. The easiest way to really tell the difference is to, again, assign the absolute configuration as S or R and then compare directly. Notice I've also switched the molecule around, so I have the carboxylic acid group on the left side here, and I have it on the right side here. So I've made a few different changes in how I've presented or oriented the molecule. So this, let me just tell you, this has the S configuration, and this one has also the S configuration. So that's the SS molecule. This one has the R configuration, and this one also has the R configuration. Okay, so the relationship between these is enantiomers. Both positions switched completely. All the stereocenters in the molecule are mirror images of the other, and so those have to be enantiomers. And again, we're comparing this center S with this one on the right, R, and this one in the middle is S compared to this one as R. Okay. One more example, because this one's a little tricky. It might be useful to take a look at. I have 2 cyclopentanes. These happen to have 3 groups on them, which look like this. Okay, those are CH3s. I'm just not going to write the CH3, so you know the end of a bond, it has a carbon group. And then I could write this molecule. Okay, what's the relationship? There are 3 stereocenters in the molecule, or centers of chirality, or stereogenic centers. But this molecule has a plane of symmetry. Right there. Same one with that one. These are identical. There's a plane of symmetry which bisects that OH. Meso compounds don't always have to have only 2 stereocenters. It just matters that there's a plane of symmetry in the molecule. So actually, if you just rotate this molecule 180 degrees and then flip it over, okay, and slide it here, it'll line up exactly. You'll see that these are the same molecule. So it is important to carefully look at the 3-dimensional structure and the relationships between things and look for symmetry and see what's going on. Another way to tell a meso compound, notice if I go this way around the ring, okay, or this way around the ring, actually this is not a stereocenter necessarily. It's actually a very funny case of a pseudo stereocenter, but actually that carbon doesn't have really 4 different groups attached, except for the fact that this is opposite of that in terms of its configuration. So this is a funny position, a little bit unusual. But what I would hope you would recognize here is that these 2 molecules are identical. Envisioning their 3-dimensional structure and orient them to try to superimpose everything, that can tell you. If you have difficulty seeing that, please get a set of molecular models so that you can see this in 3 dimensions and hold it in your hand. Okay, thanks for watching, and we will see you in Wednesday's class.